Hi folks, we're going to do a problem using the drag equation. Now let's talk about that drag equation before we actually do our problem. The force of drag on an object is 1/2 the drag coefficient times the density of the fluid times the cross-sectional area that is actually facing the fluid as it falls times the velocity squared. Now that is the drag equation. Here's the problem. The terminal velocity of a person falling through the air depends upon the weight and the surface area of that person. What's the terminal velocity of an 80-kilogram skydiver falling in the pike or head-first position with a surface area of 0.40 square meters? Now, when somebody is in a state of terminal velocity and they are falling, but they have stopped accelerating, so force of gravity down is going to be equal to drag force upward. Those two forces are equal and opposite when you are in a terminal velocity situation. This problem wants us to find the terminal velocity, and that is this velocity right here. That's my terminal velocity. So I'm going to do a little algebra. Velocity is going to be equal to 2 times the force of drag divided by the coefficient of drag, the density of my fluid, and the area that is being presented to the fluid, which side of the person is falling downward. And I'm going to have to take the square root of all of that. So let's take a look at my situation. The terminal velocity I am going to use for this situation. The force of drag is going to be equal to the force of gravity. So the force of gravity is the mass, my 80-kilogram mass of my person, times, to get gravity, times 9.8 meters per second squared. The problem says that my person is going head first in the pike position, so they're quite aerodynamic. If I look in your textbook for the drag coefficient, they don't have a drag coefficient for head first, but they have one for feet first. So I'm going to go ahead and use the drag coefficient for feet first, which was 0.70. This is a ratio, so there are no units on that. This person is falling through air. Typical density for air is 1.21 kilograms per cubic meter, and the cross-sectional area that is actually presented in the direction of motion for a person is 0.140 meters squared. Now, what do I mean by cross-sectional area presented as it falls? If somebody's falling like this, they're going to have a lot less drag than if somebody is falling like this with everything spread out and they got big clothes on. They're going to be really a lot draggier, kind of like a flying squirrel, and they are going to have a much bigger drag coefficient and a bigger surface area, both of which will affect terminal velocity. So if I shove all of these numbers into my calculator, I get out the other end 69.2 meters per second, which is just about 155 miles per hour, and that is because typical terminal velocity for a body is about 120. This is faster. Why? This person has a small cross-sectional area, and so they are making themselves sleek and speedy. All right, that will do for this one. See you later.